Hello everyone, good morning. Today is Tuesday. I hope you're all doing fine. Okay, so today we're going to be discussing physics, and we're going to be looking at a new topic today. But before that, I want to just tell you some fun facts in physics. Okay, so I want you to try to figure out who the person I'm going to show you now is. So can you tell me, or can you think and try to say who this woman is? Have you seen her picture before? Do you know this person? Okay, you can guess. Okay, let's see who she is. Okay, this woman is Émilie du Châtelet. Émilie du Châtelet, she was a French scientist, a French physicist, and she made a lot of contributions to the fields in science. So we're just going to look at a few of them and see how she actually made our lives easier, or how she actually improved, life as we know it. Okay, so let's see the first of them that we're going to discuss today. Number one, actually, this is the main thing that she is recognized for. This is one of the main things that she's recognized for. She translated and made commentary on Isaac Newton's book, his book containing basic laws of physics. We know, we've talked about Isaac Newton, so we know that he had a lot of contributions in physics. So Émilie du Châtelet translated his book Principia and made commentary on it. So, and there's something else. She actually postulated an additional law. Okay, I think we remember that we talked about work, energy, and power in the last class. Yeah, and we talked about how energy is neither created nor destroyed, but can be converted from one form to the other. Yeah, so it was Émilie du Châtelet that postulated that additional conservation law for total energy. Isn't it amazing? Yeah. So, and of course, we know that kinetic energy is an element of that law. So how does that help us? Like, you're probably asking, okay, this conservation law, of course, it's obvious that it helps us in the theoretical aspect of physics, understanding some things in physics, but it's also practical. It can also be practically applied in day-to-day life. One of such examples is this. I don't know if you've seen something like this before. For those of us that might be interested in electricity, yeah, this is a turbine. We use a turbine is one of the things that are involved in generation of electricity. Now, the concept of generation of electricity on its own applies the law of conservation of energy, because we convert the kinetic energy from the water. The falling water has kinetic energy, is moving. I said in the last class that when you say kinetic energy, you're talking about motion, energy as a result of motion, right? So that motion of the water produces kinetic energy, and kinetic energy is what we convert to the turbine and the generators and all that, and then we get electricity. So when you see electricity in your houses or in your offices or wherever you find yourself, you should just think about the fact that it was Émilie du Châtelet that postulated this additional law that helps us to understand that procedure. So yeah, we should be thankful. Yeah. Okay, so the next thing we're going to just discuss is the fact that she did some research, and based on her research, she published a paper on the science. She published this paper about the science of fire. She was researching about fire, trying to figure out the scientific, background of fire, and she predicted what we know today as infrared radiation. We know what infrared radiation is. It's applicable in so many of the things that we use today. In fact, if you're planning to be a soldier, or you're thinking about going into the medical field, you can't actually avoid the use of infrared radiation. So what she predicted that as at the time when she was, alive, and today we know it as infrared radiation, and we know also about the nature of light, right? So let's just say that indirectly she actually helped us to get things like the night vision cameras. The night vision cameras use infrared radiation. So yeah, indirectly she laid the foundation for components, or should I say equipment, such as this. Right? Yeah, so we should be thankful to Emily de Châtelet. Her name is very long anyway. There are some other things. I don't know how to pronounce the whole thing. Very long. Marquis de Châtelet. She was a Marquis something. Yeah, so that's Emily de Châtelet. So you can always even read more about her life, and you see so many other fun things that you would find out. So yeah, that's it for fun facts and physics today. Let's move on to what we need to do today. So there are 3 major things that I need you to know if you pay attention in today's class. You can see them on your screen. Number 1, we will try to define expansion. Number 2, we'll try to talk about the advantages and disadvantages of expansion. And number 3, we'll try to talk about the types of expansivity. Okay, so let's start with our topic. The topic is thermal expansion in solids. Thermal expansion in solids. Now, I think you might have an idea about what thermal expansion is, but if you don't, let's talk about that. What is thermal expansion? When you hear the word thermal, what comes to your mind? When you hear the word expansion, what comes to your mind? I think if you've heard any of these words before, you would know that thermal has to do with heat, and expansion has to do with something getting bigger. So we can say that thermal expansion is the increase in size, okay, it can be size, it can be volume, of a substance as a result of the heat applied. So you can see where thermal comes in. Thermal has to do with heat, expansion has to do with an increase, something getting bigger. So thermal expansion is the increase in size or volume of a substance as a result of the heat applied. Now, an example of expansion is the ball and ring experiment. Actually, this experiment was it was brought about by a professor who actually wanted to explain expansion to his students. He wanted to explain expansion, so he brought up this experiment. Now, what's it all about? You can see the ball there and a ring there. Now, before at first the ball passes through the ring freely. Now, when you try to pass the ball through the ring, it moves freely. Then when you heat up the ball, the ball expands. It's subjected to heat, so the ball expands. And then because of the expansion, it doesn't pass through the ring any longer. But then when it cools down again, it passes through the ring. So this is a good experiment to see the effects of expansion on a particular object? Yeah, on a particular object. Okay, so let's move on to advantages or applications of expansion. Now, when we say advantages, we're talking about, okay, what are the good things that we can get as a result of expansion, or what good things has expansion, or does the phenomenon expansion do for us or give to us in real life. So let's talk about some of them. I just mentioned some of them. So the concept of expansion is applied in thermostats. I don't know if you've heard about thermostats, but you have probably seen them. They help to maintain a steady temperature in heating and cooling systems. They're like regulators. They make sure that you don't go beyond a certain temperature, or way below that temperature. That's a picture of a thermostat. So you can see how it's like a regulator. If you've ever ironed your clothes, if you're a person that irons your clothes, at home, you would probably have seen that regulator on your pressing iron. Okay, that helps. You can use to adjust the temperature and all of that. That's a regulator. So a thermostat is inside heating devices, inside cooling devices, to prevent the temperature from going over a particular limit, okay, or going way below a particular limit. So that's thermostat. Very important component anyway. So let's talk about another, another advantage, or you can say another application anyway. So automatic fire alarms. Now, this is a picture of a fire alarm. right, of a fire alarm. Now, automatic fire alarms work with the detection of a change in temperature, which actually expansion contributes to. And sometimes, of course, most times they are accompanied with smoke detectors. At least all the fire alarms we currently have in use, they are accompanied with smoke detectors that also, check if there's actually smoke and all that. So, but expansion is also applied in the use of fire alarms. So you can see that's a good one. It prevents your houses from getting burned or your schools from getting burned and all of that. So number 3 would also look at riveting 2 metal plates. So if you want to put 2 metal plates together, you don't want to probably weld them together, you don't want to do welding, you can use a rivet. A very hot rivet will be pushed through the 2 plates and hammered while it's very hot. Then when it cools down, because of the fact that it was very hot when you pushed it through, it pulls the plates tightly together. Okay, so this is just a picture of rivets, small rivets. You can see that. Okay, number 4, we'll talk about removing a stopper from a glass bottle. So you have a bottle and you're trying to remove the stopper, and it just won't come off. Probably it has stayed for a while, or one or two other external factors prevents the stopper from being removed freely. What do? You can hit the neck of the bottle. You hit the neck of the glass bottle, and then the stopper actually comes out easily. Okay, so you can hit the neck of the bottle and the stopper actually comes out freely. So that's a picture of the bottle and the stopper. So you can just look at that and understand. Then we're going to move on. There are so many other applications anyway, but these are the 4 that we will be discussing for today. So let's look at these advantages of expansion. So what are the bad things? Yeah, something like that. Yeah, the things that are not favorable to us, the disadvantages of expansion. What are they? We're just going to mention a few. Okay, now it results in the deformation of bridge structures during hot weather. You know what a bridge is? Okay, that's a picture of a bridge. Yeah. Now, you actually should know that when there is the weather is very hot, there's a very high temperature. Bridges can actually be deformed. Now, for people who construct these bridges, civil engineers and the likes, they have to take into account that, expansion would occur when there's hot weather. So you can actually prevent this anyway by making the bridges rest on rollers. So if you do that, then yeah, you're fine. If you don't do that, then expansion gets you and then your bridge actually gets deformed. So they have a lot of, a whole lot of responsibility as regards that. Number 2, another disadvantage of expansion is glass tumblers. Of course, I know that this is general knowledge. You do not pour hot liquids into glass tumblers. Because if you pour hot liquids into glass tumblers and they expand, they actually crack. So I believe we all know that you do not do this. But in case you didn't know, this is another disadvantage of expansion. It's not appropriate to pour hot liquids into glass tumblers because of expansion. Now, another one is the fact that railway lines actually buckle when they're subjected to temperature changes. Okay, when you subject a railway line to a very high temperature, they actually buckle. So this is another responsibility for those that actually construct these railway lines. They have to lay them with gaps. You can see this is a picture of a railway line. So they have to lay these railway lines with gaps so that when their temperature changes, that those gaps account for the expansion, and so the railway lines do not buckle. If not, well, that will be another story. I don't think that will be a good one. So you can see this picture. I think you know what these lines are. Okay, these are lines that can actually transmit electricity. Okay, these are lines that transmit electricity. So these lines actually snap. Telegraphic lines, metal wires, they actually snap under very high temperatures. So when you're trying to fix or connect these lines, you should take into account expansion also. Okay, that's why they actually leave a little sag, they allow a little sag. Now the sag is calculated not just with expansion. There are other variables, of course, that determine how much of the sag they would leave. But if the sag is not applied, then when there are high temperatures, the lines will actually snap. So that's another thing we need to take note of. Okay, then I think that will be all for the disadvantages. There are others, so if you're interested, you can always check more and read up more on the disadvantages. So let's talk about the bimetallic strip. This is a very important component in a thermostat. I think we talked about the thermostat at the beginning. Yeah. This is a very important component in the thermostat. Now, as the name implies, it's made up of two different metal strips of different expansivity factors. You can use copper or brass and then steel. And when the bimetallic strip is heated, it bends. It bends because these metals expand differently, and that bending is what helps to move the thermostat. So it's positioned in such a way that it can regulate the temperature. So this is the major component, or one of the major components in a thermostat. Now, how does it actually bend? The metal with the higher coefficient, the one that has a higher coefficient of thermal expansion, is on the outer side when you heat the bimetallic strip, but it's on the inner side when you cool the bimetallic strip. So just take a look at this picture. You can see we made use of brass and steel here. That's the normal way it looks when it's not heated or cooled. When it's heated, you can see that brass is on the outside. When it's cooled, you can see that steel is on the outer part. So that's just a little knowledge about the bimetallic strip. Okay. Now, I want us to go into expansivity now. Like I said, that will be the third thing we are going to discuss. We have three types of expansivity. We are going to talk about the linear expansivity, which of course has to do with length, and then we'll talk about the area or superficial expansivity, which has to do with, of course, area, and then we'll talk about the volume or cubic expansivity, which has to do with volume. So let's start with linear expansivity. Okay, what is the linear expansivity? We represent the term linear expansivity with the symbol alpha. You can see the alpha symbol in blue. So the linear expansivity alpha of a solid body is the fractional increase in length per unit length per degree rise in temperature. Now, what does this simply mean? It means that linear expansivity is a factor of three different components, which are the increase in the length as a result of the heat applied. Then we would also take into account the original length of the body, and then we'll take into account the rise in temperature. Okay, so these three things are the components that make up the linear expansivity of a body. So this is an example of a solid. You can see the original length L, and then there's an extension E that results because of the heat applied. So that extension is actually a function of linear expansivity also. Okay, so let's talk about it mathematically now. So alpha equals increase in length over original length times change in temperature. Okay, so those are the three things. You need to understand this so that you don't start cramming the formula, so you can understand how we actually obtained these parameters. So alpha here would be L2 minus L1 over L1 times delta theta. Okay, change in temperature is delta theta here. Original length is L1, so increase in length will be L2 minus L1. Also, you need to take note of the fact that the unit of alpha is per Kelvin. Okay, so now we're going to cross multiply here. We have L2 minus L1 equals alpha into L1 times delta theta. Okay, so then we can take L1 to the other side, so that becomes L2 equals L1 plus alpha L1 delta theta. Some of us might not like math, but this is not hard. It's easy. We're just taking, we cross multiplied here, and then we're just taking L1 to the other side here. So don't think we're doing some kind of magic. Then in the next step, we're going to factorize. You can see that L1 is common. L1 is here, L1 is here also. So we're just going to bring up L1 and we have 1 plus alpha delta theta. So this is the formula for getting L2 in, for getting the new length when you talk about expansivity. So let's talk about how we can apply this formula in an example. So for example, you're probably a civil engineer and you need to lay iron rails, and these iron rails are 8 meters long, and you want to lay them close up, end to end. And as at that time you're trying to lay those iron rails, the temperature is 30 degrees Celsius, and then you can already predict that, okay, there's going to be an increase in temperature to 60 degrees Celsius. So the question for you is, what gap would you leave? What gap would you provide so that when the temperature actually increases to 60 degrees Celsius, you do not actually lose every thing that all the work you've done? So that's what we want to calculate now. So I want you to imagine that you're in this position. So you have to note, first of all, that the linear expansivity of iron is 1.2 times 10 raised to the power minus 5 per Kelvin. Okay, now let's talk about all the parameters that we have. Okay, alpha is, we've said what alpha is. Then our delta theta, now that there's a change in temperature from 30 to 60 degrees Celsius. So 60 minus 30 is 30 degrees Celsius. So the change in temperature, is 30 degrees Celsius. Okay, so L1 is 8 meters. 8 meters, okay? So L1 is 8 meters, and we are looking for the gap, so that's L2 minus L1. That's what we're looking for, right? So let's call back the formula that we derived before, and let's see. So L2 minus L1 is actually alpha into L1 delta theta, right? So let's just substitute. It's as easy as that. So 1.2 times 10 raised to the power minus 5 times 8 times 30. Okay, and this gives us what? 0.00288 meters, or you can say 0.003 meters. Okay, and if we change that to centimeters just to make it more compact, we can multiply by 100 and we get 0.3 centimeters. Okay, so you can see that the gap is very small, right? 0.3 centimeters compared to 8 meters is very little, right? But sometimes it's just that little factor that can destroy all the work you've done. It's just that little, not leaving that little gap that can make a whole railway line, buckle, or that can deform a whole bridge structure. So there's a big responsibility for you to actually understand this. Let's go on now to area or superficial expansivity. Like as the name implies, it's exactly the same thing as linear expansivity, but instead of considering the length of the body, we are considering the area of the body. So the area of superficial expansivity is represented with the symbol beta. So it's the fractional increase in area per unit area per degree rise in temperature of a solid surface. Okay, so let's just look at the mathematical expression. So wherever you had length before, you would have area now. So increase in area over original area times change in temperature. So beta here will be A2 minus A1 over A1 times delta theta, and the unit of beta is the same as that of alpha. Now, but there's a peculiar relationship between beta and alpha. You can see beta is 2 times alpha. Now, if we cross multiply, we have A2 minus A1 equals beta into A1 times delta theta. Then if we want to get A2, we say A2 equals A1 plus beta A1 delta theta. And then we say A2 equals A1 into 1 plus beta delta theta. So that's the formula for area superficial expansivity. Then we can talk about cubic or volume expansivity. It's exactly the same again as linear, but in this case we're considering the volume of the substance, or volume of the surface, or volume of the solid. So now it's the fractional increase in volume per unit volume per degree rise in temperature, and it's represented by the symbol gamma. Okay, so we can say mathematically that it's increase in volume over original volume times change in temperature, and gamma is V2 minus V1 over V1 times delta theta. The unit remains per Kelvin. And there's a relationship between gamma and alpha, and gamma is equal to 3 times alpha. That's 3 alpha, okay? So if we do the same thing here, V2 minus V1 equals gamma V1 times delta theta, and V2 equals V1 plus gamma V1 delta theta, and then V2 equals V1 into 1 plus gamma delta theta. Okay, so let's go on to a second example. So in this case now, you have an iron cube that has 15 centimeters as each edge, and it's 20 degrees. The temperature currently was 20 degrees Celsius, and you need to get the new surface area, okay, because now the temperature has increased to 80 degrees Celsius. You also need to get the new volume, okay, because of that temperature increase. So we still have to note that the linear expansivity of iron is 1.2 times 10 raised to the power minus 5 per Kelvin. Then we can go ahead and list out all our parameters. So for the first part of the question, we need to get beta because we're considering an area now, not the length. So beta is 2 times alpha, and that was what we did here to get 2.4 times 10 raised to the power minus 5. And then our change in temperature is 80 minus 20, yeah, because the new temperature is 80 degrees, so that's 60 degrees Celsius. Then the original length was 15 centimeters. The area also, the initial area will be, L square, which is 15 times 15, which is 225 centimeters square. So we have to find A2 now. How do we get A2 now? So let's just bring back our formula and substitute. It's as easy as that. So we have 225 into 1 plus 2.4 times 10 raised to the power minus 5 times 60. And that gives us 225 into 1.00144. And that gives us 225.324 centimeters square. So that's that for the area. Now, it's important that you understand this formula. It's the formula that actually matters because that's what you use to solve the question. So let's do the second part of that question, which is the volume that we need to find, right? In this case now, we'll be talking about gamma since we're looking for the volume, and that will give us 3.6 times 10 raised to the power minus 5 per Kelvin. So when we get the temperature change also, it remains 60 degrees, of course, and our length is still 15, so our volume would be L cube, right? So that's 15 times 15 times 15, which is 3375 centimeter cube, okay? So V2 is what we're looking for, so let's bring back the formula that we derived. So V2 equals V1 into 1 plus gamma delta theta, so that gives us 3375 into 1 plus 3.6 times 10 raised to the power minus 5 times 60. And if you multiply that with, taking into account BODMAS, multiplication before addition, okay, don't forget that. That should give us 3375 into 1.00216. Okay, so that gives us 3382.29 centimeter cube. Okay, you can take a deep breath now. We are done with this particular example. Okay, but I want just to quickly touch on this and then we can end for the day. Relationship between temperature and density. What's the relationship between temperature and density? I think we need to study this because in our next class we'll be talking about something else that might be related to this, yeah? So just listen up. So the density of a body varies in inverse proportion with its temperature. I believe you've done inverse proportion in grade 9. Yeah, so you remember that when they say something varies in inverse proportion, it means as one increases, the other decreases, right? Yeah, so as temperature increases, the density reduces. Now, that is the normal, that's what we expect. There are some, okay, let me not give you the gist yet. You'll find out next week. But let's just say that as the temperature increases, the density reduces. Yeah. That's what you need to know for now. Okay, so mathematically, we can actually say that D2, D stands for density, D2 equals D1 over 1 plus gamma delta theta. Yeah, that's the way we express that. Then we know that D2 is final density, D1 is initial density. Of course, we know that gamma is the cubic expansivity, and we know that, of course, delta theta is change in temperature. So let's just look at the question on that. What is the density of brass at 60 degrees Celsius if the density at 0 degrees Celsius is 15.2 gram per cm cube? We have the linear expansivity of brass here. So, but remember that the formula actually needs us to use the cubic expansivity, so we have to do some manipulations there. But let's list out all our parameters. D1 is 15.2 gram per cent cube. Alpha is 1.9 times 10 to the minus 5 per Kelvin. Yeah, so gamma will be 3 times alpha, right? So 3 times 1.9 times 10 to the minus 5 gives us 5.7 times 10 to the power minus 5 per Kelvin. And delta theta is simple and very straightforward. Yeah, 60 minus 0, just 60 degrees Celsius. So, and D2, yeah, D2 is what we're looking for. So let's just call back the formula that we derived. Okay, we didn't derive that. Maybe I'll tell you how to derive it some other time, probably. Yeah, if you're interested in that. So 15.2 over 1 plus 5.7 times 10 raised to the power minus 5 times 60. Okay, and that would, if you do that, you know, taking into account everything that needs to be done, you would get 15.2 over 1.00324. So I'm sorry, 342. That gives you 15.1 gram per cm cube. Now you can see that the change in density is very small, right? For such a wide range of temperature, 60 degrees. But yeah, that's how it is. But the point is, as the temperature increases, the density reduces. That's what we want to just take note of. So there, summary. Let's talk about a summary of everything we've done. We started from, you know, the definition of thermal expansion. We talked about, you know, the advantages, the disadvantages, before we then moved on to linear expansivity, then area expansivity, then volume or cubic expansivity, and then finally we talked about the relationship between density and temperature. Now remember, we also talked about Émilie de Châtelet. You can read more about her online. So I always say that it's important that you practice. So I'm going to show you some questions that I want you to solve. Okay, so try to do this. And if you can get these questions, please reply and send me your answers. And let me just know that you understand everything we've talked about. Now, you're to state 2 applications of expansion apart from the ones I mentioned. So don't try to be smart and mention what I have told you. State 2 applications of expansions apart from the ones in this video. And a copper cylinder is 6 centimeters long and 3 centimeters in diameter at 30 degrees Celsius. So you're to find its length, its area, and its volume when it's heated to 85 degrees Celsius. Okay, so you can also visit quizzes.com. Okay, you can also visit quizzes.com and play some games on thermal expansion. You have a lot of games on different subjects on quizzes.com, so you can just search and play some on this particular topic. So remember to send a comment on what you might not understand, and also remember to like and share and subscribe for updates. Okay, so I'll see you guys again same time next week. I hope you continue to have a lovely day. Bye bye. Hello everyone.